So in this lecture, we'll finish Chapter 9 and begin Chapter 10. So we will have our Chapter 9 quiz on Wednesday when I get back from seeing the eclipse. So please make sure that you watch through this whole thing, get the notes updated, because we will pick up where it leaves off on Wednesday. So we were talking about tides last class, and we said that we have 2 high tides and 2 low tides per day. And the reason for that is due to the moon's gravity pulling on Earth and creating what's called tidal bulges on either side of the Earth, one facing the moon and one on the exact opposite side. The reason for that is that the water behaves sort of like a stretchy material, where if you pull a bit harder on one side than the other, it tends to stretch out. The reason we see high and low tides is because while that tidal bulge remains pretty fixed, the Earth rotates beneath it. So us sitting on the Earth will be at a certain point at some time, but 6 hours later will be 90 degrees around. And if we were at high tide at first, that's going to put us in the low tide region. If we wait another 6 hours, then although the tidal bulges are still in the same spot roughly because the moon has not moved very much during that time, we will have again rotated about 90 degrees. And so we'll be back at the high tide, and then after one more 6 hour interval, we will be back at low tide. 6 hours after that, we'll just be back to the top picture. And so this is why we alternate between high and low tide and why we have them roughly 6 hours apart. So roughly every 6 hours. Now, in reality, it's not quite that perfect, and I'm going to show you a couple reasons why. All right, here's our alternation between high and low tide, because we are on the rotating Earth while the tidal bulges do not move very much. Now, keep in mind that that doesn't mean that the water is stuck in place. That just means that whatever water is facing the moon as the Earth rotates around is going to be pulled out like that, and then go back down as it continues rotating away from the moon. But the reason it's not perfectly every 6 hours is because we have ignored that the moon itself is moving as the Earth spins. As the Earth rotates and the moon moves around it, the position of that max tide is a little bit ahead of where the moon actually sits. The other thing that affects this is that the sun is also pulling on the Earth and the water around it. And so we get this extra tidal effect from the sun, that is the orange ring, the solar tide, and that adds or cancels out a little bit with the lunar tide. When they add together, which happens here, you get the spring tide. When they cancel out, which happens here, you get the neap tide. The spring tide is the highest tide of the year, the neap tide is the lowest. And you can see, since it takes about a month for the moon to orbit the Earth, that we have about 2 spring tides a month and 2 neap tides a month. So 2 high tides, 2 low tides a day, 2 spring tides, 2 neap tides a month. So one question we could ask is, why don't I see tides happening? Why don't I see waves crashing in ponds? And it's because if we remember that tides are from this difference in gravitational pull, you'd have to think about the difference between the top and bottom of the pond. Ponds are shallow. There's not a lot of water there. They don't cover a lot of area. So we don't get tides just because the ponds are too small for those forces to be significant. We don't see enough difference in gravitational pull, and that difference is what's important. We don't feel tidal forces from the moon ourselves for the same reason as for ponds. We're just too short. We'd have to think about the difference between the gravitational force from the moon on our head versus on our feet. And they just aren't different enough because we're not tall enough. We'll talk about black holes in a bit, and there you get enormous tidal forces to the point that even we begin to stretch if we were to fall into one. And that process is called, and this is the real term, spaghettification. So there are enormous tidal forces in black holes that cause you to stretch out like a piece of spaghetti. All right, so sort of the elephant in the room on gravity that we've never really had a chance to talk about is that it's kind of weird compared to other forces. You see friction happen when two things rub together. You see normal forces when one thing sits on top of another. You see forces from impacts. You see tension when a rope is connected to something. Gravity is different in that it's happening over a long distance without any direct contact between the objects required. So the Earth is pulling on the moon right now, but they're not touching each other. That is pretty odd compared to the other types of forces. So the explanation we come up with for that is that there's an intermediary, something between the Earth and the moon that sort of transfers that force. We call that thing a gravitational field. And we say that that's sort of a bed that the moon sits in that is created by the Earth. And through interaction with that bed, that is how the moon feels a gravitational force. I know it's a little disappointing to find out that's all a force field is, but we also talk about electric and magnetic fields for similar reasons. How we represent them is with what are called field lines. They're like vectors, they just indicate the direction of this gravitational field, and it's just the direction that mass tends to be pulled or pushed by the Earth. And we know that things are always pulled by gravity, so the field lines point towards the Earth. And I'm going to try and kind of evenly space them. So this is what Earth's gravitational field looks like. It's pretty symmetrical since the Earth itself is roughly a sphere. But the field lines are useful not only for this sort of picture representation, but for quantitative stuff. They tell us which way the field points, but also how large it is. If you're here versus out here, in that first region, you're going to feel a much stronger gravitational force from the Earth than in the second region. And we notice that's also where the field lines get closer together. So the density, the spacing of the field lines is telling us how strong the force of gravity is where you are. If you're in empty space where there are no masses like this creating gravitational fields, you won't see any field lines. In other words, they're infinitely far apart and you feel no gravitational force at all. Now, another wrench in the works is that everything we've said about Newtonian gravity, meaning based on Newton's law of gravitation up here, all of that is actually only half true, which at this point in the chapter, maybe that's a little bit upsetting to find out, but that's how all of the history of physics has gone. We just get a little bit closer each time. So, Albert Einstein began to think back in the early 1900s about some of the consequences of Newton's laws. For one, we never saw any time dependence in that law of gravitation, which would mean that gravity is something that can act at any distance instantly. There is no time it takes for gravity to get from one point to another. Through other research, he had concluded that things should not be able to travel instantly like that. At most, things should be able to travel at the speed of light, because that's the speed that things travel at when they have no mass. So, he realized something was a little bit wrong with Newton's law of gravitation. His proposed fix was something called general relativity. It is a little bit upsetting compared to Newtonian gravity because of what it says gravity is. It actually doesn't say that gravity is a force anymore. It actually rejects that idea that gravity is a push or a pull. Instead, it's sort of a change in the playing field itself, what we call space-time. It's 4D because we have these 3 dimensions of space and 1 dimension of time, but motion makes most sense when we talk about the two as one inseparable object, space-time. And the visualization that's usually given for Einstein's idea of this warping of space-time is what I'm going to show here. So they show this stretchable fabric, and if there is no mass present, you see that it's flat. But when you place a large mass in it, you will see the structure of space-time warp. This is what gravity is in the view of general relativity. Not a push or a pull, but just this playing field, this space that everything lives in, changing. And that affects how things move because now they're moving in a new space. You'll see him drop something and it'll move towards this mass, now not because of the idea of a pull, but because that's just the natural way something would move in a space shaped like this, towards the center. And if it has this speed to it, tangential speed, instead of falling in, it'll orbit around. And so that again is not that something's being pulled towards the Earth, it's just moving the way it would naturally move in this space if it has some speed to it. So that is the idea of general relativity. It's that when you have something very massive placed in a region, it distorts that space. And so even though there's no force present, and so things should move in a straight line, what a straight line is changes when that mass is present. So we know, due to their inertia, things move in straight lines at constant speed as long as no forces act on them. When something enters a region like this that is warped, it still travels in a quote-unquote straight line. But a straight line's definition has changed because the space itself has changed. So this would still be considered from this view an inertial path, not something due to a pull. That's the idea of general relativity. Gravity isn't a force, just a distortion of space-time of the playing field that everything is living in. Space-time distorts the straight line or inertial paths that things naturally travel on, including us. And it takes a very long time to wrap your head fully around that idea. I'm going to post on Canvas what I think is a better visualization than that stretched fabric one. It explains some of the issues with that visualization and gives you a way to think about it that I think is closer to the truth of general relativity. So that'll be up on Canvas. But keeping in mind that Newton's laws are not perfect, that they're an approximation, we can still figure out more things with them. So we're going to jump back to universal law of gravitation, the Newtonian view, and we'll use it to explain the idea of a black hole. So black holes come from stars that are dying off as they radiate energy in the form of heat and light. And as that happens, the gravitational pull tends to condense the star down and down and down. And under the right conditions, that condensing can make it so that the star becomes very, very compact, very dense. If you yourself were standing on the surface of that star, which let's pretend you're invincible and you can do that, you'll feel a certain force when the radius of the star is, let's say, r. But if it shrinks to half that size because of this inverse square law, you would feel 4 times the force. If it got even half as large as that, you would feel another 4 times or 16 times what you started with, and so on and so forth as the star shrinks down. And that's why black holes are these regions of really intense gravitational pull. The smaller that distance is, in this case the radius of the star, the larger the gravitational force gets. Now, in truth, the mass of, we could say mass 1, the mass of the star itself, is changing as this happens. It's just that this reduction in distance is much more dramatic. The radius falls off quicker than the mass of the star does, and so we do see this force increase. If it shrinks down enough to within what's called the event horizon of the star, then the pull of gravity is so strong that nothing can escape, even light. And this is something that Newtonian gravity can't predict, because it would say, since light is massless, it doesn't feel a gravitational force. But from the general relativity view, all that's happening from light being pulled in is that it's traveling along a new inertial path. It doesn't need mass to do that. It's just traveling in what we would consider a straight line in that space. So general relativity predicts that there is a certain gravitational field, a certain warping of space-time in which even light gets stuck in these orbits. But if light cannot escape that region, it can only either orbit or fall into that black hole. That would mean that we're not seeing the black hole. We see things because light enters our eyes, but if light can't escape a black hole, there's no way for us to see it. So even though they're called black holes, they're actually invisible. And you've probably seen some quote-unquote images of black holes, but what you're really seeing is kind of what's around the black hole. You'll see some kind of dust clouds and some light around it, and that light is orbiting this invisible center. We can't see the actual black hole, just what's surrounding it. Now, you'll often hear that if the sun became a black hole, we'd be in a lot of trouble. It turns out that's not the case. So if we think about this shrinking distance, it's about us sitting on or near the star. The Earth is a certain distance away from the sun. And just because the sun got smaller, unless it suddenly gains a lot of mass, we are not going to see that same increase in force on us because our distance from it is not changing. The only way we would be in trouble is if, from turning into this black hole with this strong pull, the sun starts to accumulate more and more and more mass until the gravitational pull is significant enough to have us start spiraling in. But that is not the situation, and in fact we know it because at this point we know that at the center of every galaxy we've looked at, there is a huge black hole present, including our own, the Milky Way galaxy. And it has been there for who knows how long and has not destroyed the galaxy. So far we're okay. All right, and to finish off chapter 9, there is this idea of, again, universal gravitation, Newton's laws. They are approximations, but they're very good approximations that led to some very important discoveries. So there are things that Newton's laws can't fully describe, including black holes and things like what is called dark energy. That is the idea that from more recent astronomical observations, the universe isn't actually static. It is accelerating outward, meaning everything's getting farther apart from everything else, and that's happening at a faster and faster rate. Expansion alone wouldn't indicate that there's something pushing outward, but the fact that we're accelerating outward, that does mean there's a push. And so we don't know where that's coming from. We can't find the source of the push, so we call it dark energy, unobserved energy. Similarly, if we look at the rotation of galaxies, that depends in part on the mass of the galaxy. But the rotation rate we'd predict based on the mass we can see is not at all in line with the actual rate of rotation or other properties of the galaxy. What would have to be true for the measurements to line up is there would have to be a lot more mass than we can actually see in the galaxy, we can actually observe. And that's across all wavelengths. It's not a thing of visible versus invisible parts of the spectrum. We've looked in many different parts. We just can't observe where that extra mass is coming from. And so it is called dark matter. So when you hear dark something in physics, it usually means something we don't understand very well yet. And Newton's laws can't do anything about those, and even general relativity has not explained those fully. But in its time, the law of gravitation was extremely important because it led us to discover things for the first time. For one, it explained why planets are round. It's the idea that if it were a cube or something like that, then you would have these closer parts kind of compact inward, and that extra mass pulled inward would start to pull the corners inward. And the only way this is all going to stabilize out into something that doesn't pull further inward is if you have no sharp points. You only have this sphere, and then everything is equally far from the center of the sphere. You don't have some parts being pulled harder than others. But what's more interesting to me is the law of gravitation. It's the first equation to predict the existence of a planet. Astronomers used this equation. They looked at the orbits of the planets and they said, if this equation is true, the planets should orbit in such and such a way. But they don't. The only way that this equation could be true is if there is an extra planet present altering the orbits of the others just a little bit, perturbing them. And based on Newton's law of gravitation, they predicted the mass of this planet, they predicted where it should be in the night sky, and they looked for it. And they found it. It was Neptune. So Neptune was not found just by looking through a telescope and finding it out there among the stars. It was predicted. They used math to find it. Similar for Pluto. And to me, that's pretty amazing. Yet another win for physics. That's a deep dive into gravity. We're going to look at another aspect of it here in the next chapter, and that is projectile and satellite motion. We come back to Earth for this one for a little bit, and we think about why projectiles move the way that they move, meaning you throw a ball, you fire a weapon, you drop something off a cliff, a car drives into a ditch. Anything that is under the influence of gravity alone, we call a projectile. A launched object under the influence of gravity alone. And that may sound a lot like free fall, and it is because it is. Free fall is a special case of projectile motion, where you have no horizontal motion, just vertical. So we already know that gravity affects the speed of things that are falling. It also affects the path they move on. By that I mean if gravity weren't present, things would move in a very different way. If you launched a projectile in empty space, it would just continue in a straight line because that's what its inertia tells it to do. In the absence of a force like gravity, things move in straight lines at constant speed. Gravity tells it, no, you change your path, you change your speed, you accelerate. And so, instead, you would follow a curved path like this. And that lets us see what gravity does to projectiles, comparing these two paths. So this chapter is largely the study of that, projectiles, things like cannonballs, pretty much any sport involves a projectile, bullets, waterfalls, all sorts of things where stuff's falling just under the influence of gravity. And it's going to be easiest to think about if we separate it into vertical and horizontal bits. That's the idea of using components of a vector. So if we throw something, follows this arc, and we could look at the direction it's moving at any point on there, talk about its tangential velocity. That's which way it's going right at that instant. We can break that into two pieces, a horizontal component and a vertical. Okay, so that is from chapter 5, the idea of vector components. And in doing that, we can break projectile motion up into two much simpler motions. We're going to start by looking at something rolling off a table. That would mean it's launched not at an angle, but horizontally. That's the easiest place to start. So we know that gravity pulls downward, and that means that really the only interesting things happen downward. If the force is pulling that way, that is the direction of acceleration. Anything happen horizontally is unaffected. In other words, horizontal velocity is constant. And so, if we just focus on rolling something off a table and think about just its horizontal motion, it's going to cover the same distance from 1 second to the next. It's not going to speed up or slow down horizontally because there are no forces acting horizontally to make that happen. Vertical is going to look just like free fall, which is that something speeds up as it falls by 10 meters per second each second. Vertical velocity increases due to the downward pull of gravity. And so that's saying in the first fraction of a second, this ball might fall that much. In the next fraction, it's going to fall a little bit more and a little bit more and a little bit more because it's speeding up as it falls by 10 meters per second each second. Now here's the cool part. If we put those ideas back together, okay, so if we think about them separately, the vertical and horizontal motions are not so hard to figure out. Horizontal is just constant speed, you're covering the same distance each second. Vertical is like the free fall stuff we've already talked at length about. So projectile motion, the actual motion we see if we roll something off a table, is just a combination of those. You smash them together into one motion. And we do that by sort of tracing across. So the ball first leaves the table. It's going to be at the height of the table, but shifted over to the right a little bit due to its horizontal motion. After another fraction of a second, it's going to have fallen a little bit, but also it will have shifted to the right just a little bit. And that's going to put it here. After another fraction of a second, it's going to have fallen a little bit more, but shifted right a little bit more. It's shifting to the right by the same amount each second. After another little bit, it will have fallen down even more. That distance is getting larger, but the horizontal distance it's covering is not changing. And then one last little bit later, it will have fallen even farther, but it will be even farther over to the right as well. So by combining those pretty simple horizontal and vertical motions, we get the real motion of the ball. We see that it follows the arc we'd expect. So that's the use of vector components here, is they let us think about two simple motions rather than one seemingly complicated one. The name of that curved path, by the way, is a parabola. Just like for math class. That's why it's useful to learn about them. So the idea of that is that you can treat vertical and horizontal motions separately in that they don't affect each other. The fact that this ball is falling does not affect that it's moving horizontally, or vice versa. So with that in mind, see if you can try and answer this question. Go ahead and pause the video, look at it for just a second, and decide. Alright, so if you thought that both hit at the same time, you are correct. Now, I agree, this one's going much faster as it gets launched to the right. But, as we said, the horizontal motion of the ball should not affect its vertical motion. In other words, its vertical motion should be exactly like the dropped ball. And so, sure, it may cover a large horizontal distance from 1 second to the next. But in doing that, vertically it is keeping up with the dropped ball. So, after 1 second, the dropped ball will be at the same height as the launched one. After another second, still about the same height as the launched one. After another, same height. But we see that the distance between those is getting larger and larger. These are like taking snapshots as the cannonball moves horizontally. But if we look at vertical snapshots, both are going to be at the same height at the same time. And to prove that to you, I've got a video over here that shows that idea with this spring mechanism. So he sets the spring. You may notice on the left end of it, there's a stick poking out. On the right, we've also got a platform for a ball. And so he's going to put a ball with a hole in it on the left side, and then a ball on the platform on the right. When he releases the spring, the ball on the left is going to fall. The ball on the right is going to get launched horizontally, like being fired horizontally out of a cannon. And we're going to see which one hits first. So even by the sound of it, you can hear that they're hitting at the same time. And again, that says that even though one ball is moving horizontally, doesn't matter. Its vertical motion is just the same as if it were in free fall or being dropped. So that's something being launched horizontally. Let's look at something being launched at an angle now. Even though it's launched at an angle, the acceleration due to gravity is still straight down. Gravity is still pulling the object straight downward, not at an angle. The effect that has is pretty much just to tilt up or down the path of the projectile compared to the horizontal motion. So just like with the horizontal launch, if you launch something upward at an angle, the horizontal distances are the same because there is nothing to speed up or slow down the ball horizontally. Same if you throw something downward at an angle. Horizontal distances, still the same. Horizontal motion doesn't change from 1 second to the next. The vertical motion is still like free fall even if you throw something at an angle. It's just that the location the ball is at any time is shifted up by that angle. So, if you were to throw something horizontally, its vertical motion looks just like regular free fall. If you throw it at an angle, it's still going to look like that free fall, but like I said, shifted up by the angle you threw it at. And so the ball will be a little bit higher from one moment to the next compared to if you had just dropped it or thrown it horizontally. If you throw something downward, it's the same idea. It's just instead of it going up, it'll be a little bit farther downward than what free fall would predict after each second, because you gave it a vertical component to its velocity in addition to what gravity was doing to it. Okay? So the vertical position of an object is just shifted up or down relative to where it would be if it were dropped when you throw something at an angle. That's the only effect it has. The last thing I want to talk about for this lecture is this idea that all gravity is doing is pulling stuff away from the path they would go on if it weren't there. We can think about and calculate things about gravity very similar to ways we already have. So let's look at this picture on the left first. If we know the speed of fired cannonball at one moment, we can still predict it at any other almost as easily as we did back when we were talking about free fall, which would be throwing something straight upward and then watching it fall. In that case, we saw it change by 10 meters per second each second. Let's say here we've got a cannonball fired at 50 meters per second. And we'll say the angle is such that the horizontal component of that motion is 30 meters per second, and the vertical component is 40. What that means is that after 1 second, this cannonball will have moved to the right by 30 meters and upward by 40 meters, approximately. So if it maintained those speeds for a long period of time, it would be moving by the right, or to the right by 30 meters each second and up by 40 meters each second. We said that the horizontal motion is not affected by gravity, and so it doesn't change. It'll still be 30 up here, 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 and here. All of those horizontal bits are 30 meters per second. The vertical, we've said, is just like something being dropped or thrown up or down. It's just like free fall. And so after 1 second, see if you can predict how fast it's moving upward vertically. Do you get that it is 10 meters per second less? So 30. And then up here 20. And then 10. At the very top, it has a vertical speed of 0, but a horizontal speed of still 30. Horizontal doesn't change. And then as it falls, it'll gain 10 meters per second each second. So by the time it's back at its original height, it is now moving to the right at 30 meters per second and down at 40. You can put those back together, that's finding the resultant to get the overall, and you will find that overall is moving at 50 meters per second, just like when it was launched. And you could do the same for any other point to figure out exactly how fast the ball is going at any of them with the Pythagorean theorem. Just like in free fall, I'm going to add vertical right here. The change in vertical speed each second is gravitational acceleration times time. So I'll write y for vertical. That's just saying that to figure out the vertical speed, after 2 seconds, it's 2 times about 10, and so it'll change by 20. If we wanted to figure out how many seconds it takes this cannonball to reach the top of its arc, we just look at its vertical speed, 40, and we would see that it takes 4 seconds to reach the top, 40 over 10. Now distance, we said back when we were talking about free fall, that the distance something falls is given by this expression. Is that still true? The answer is again yes. So we think about this is the path a cannonball would go on if no gravity were present. It would just keep going in a straight line at constant speed forever. Gravity pulls it away from that path into this arc, this parabola. And if we track how far the ball has fallen below that straight line it would go on without gravity, we see a familiar trend. After 1 second, it falls about 5 meters. After 2 seconds, it falls about 20 meters below that path. And after 3 seconds, it falls about 45 meters below. Those are all obeying this equation right here. So just like in free fall, something launched at an angle, a projectile, is falling below the path it would go on without gravity by this amount. In free fall, where it would go if gravity weren't present is nowhere. It would just float. And so this equation says instead of floating, it falls by this amount each second. The picture on the right says instead of going in a straight line forever, which is what this projectile would do without gravity, it drops by this amount each second. So here's a question. Say you had a target up here. You're trying to hit something, and right as you fire the cannon, that target falls. So there's a little trigger so that it will drop as soon as the cannon's fired. to account for the fact that it's falling, should you still fire straight at it? Should you fire a little bit above? So like this, or a little bit below, like that. What do you think? I'm going to pull up a video and show you what happens, so make sure you've got your guess. We're going to have something where we aim right at the target and then release it right as the cannon is fired, and we'll see if it hits a little bit too high, a little bit too low, or still right on the money. Although the target fell by some amount before the cannonball reached it, so did the cannonball, or the steel ball bearing they were using. That is still the idea that gravity deflects everything the same way. So if it takes this target 3 seconds to fall, it'll have fallen 45 meters, and the cannonball will have gone 45 meters below its path. So it'll still run right into the target. So the best thing to do to hit that falling target is to aim right at it, not above or below. That's where we'll stop for today. So we'll have our quiz on Chapter 9 on Wednesday. I'll see you then.